Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RIW. This is podcast 12 Bravo, which is the second half of our two-part series on BalUns, UnUns, and common mode chokes demystified. So let's talk about CMC and TLT design. CMC design. First thing we want power rating, which is maximum at your operating mode. We need to choose the type of CMC. Is it a snap-on ferrite? Is it a toroidal? Is it an ugly BalUns? Is it something else? We want to decide what toroid size we want to use for the core. Mix 31 in all cases. What's the wire gauge and type? Is it insulated? What's the voltage, standoff voltage of it, breakdown voltage? Or are we using coax? But we don't recommend enameled magnet wire because with a bifilar winding, which is typical with CMCs, both sides of the RF, the outgoing and incoming signals, are developing a high voltage across there, and a little nick in that enamel will create arcing and shorts and will mess up your SWR and your output power. And then the winding pattern. Are we going to do a crossover for inline, or are we going to do a continuous winding all the way around the toroid? We saw this in the previous session, and again, this is just a quick review of the CMC power handling budgets, which are typically much higher than on a transformer, a TLT. Because TLTs actually do more work because they're converting that impedance, and therefore there's more losses and heating effects. Whereas a CMC, there's very few heating effects or losses. Insertion losses, as you'll see, are very, very small in CMCs. Not so much in TLTs. There can be significant insertion losses on TLTs. So CMCs can have much higher power handling for a given core. On TLT design, the toroid size, in other words, more cross-section is better. Fatter, thicker walls, in other words. We want to use mix 43. A large inner wall diameter handles more turns. Okay, that means we can stack those insulated wires up next to each other. We can stack more of them all the way around. Then we remind you how to test those toroids for the mix. Remember, the mix 43 has no conductivity, whereas the mix 31 does. Decide what kind of device you want, a BalUns or an UnUns. Select the total number of turns and the ratio. Select a wire gauge from the table above. And remember, you want to have pretty good insulation. So you do have lower interturn voltages than on a CMC, but you still need some insulation there. And then good construction practices, as we'll see shortly. Now, CMC and TLT mounting. A lot of people take this very casually or very capriciously, but you have to think about some things, especially with TLTs, which do dissipate a lot more heat than CMCs. Do you have conductive? Are you heat sinking this somehow? Is there enough airflow around your toroid? And is there enough open air so that it can radiate any excess heat when it does start to get hot? How rigid is it in terms of the toroid itself and the connections? Have we strain relieved the connections? Then core stacking. If we're stacking cores to get extra power handling, then are we leaving an air gap between them to dissipate some of that heat convectively? And then connection posts and terminals. We want to make sure those are secure. Again, is a review of the TLT power handling budget table. So let's talk about limits to the toroid TLT performance, because the TLTs will, like I said, generate a lot more heat than CMCs. Now, wire resistance is not that critical because we have such a short length. We're only using 6-7 feet of wire, and typically in most TLTs. and so the resistance and the IR drop and I squared R power loss is pretty small. Can pretty much ignore it. The wire coupling to the toroid, we want those turns nice and tight. If we get them really loose, it's not going to be as efficient. The core coverage with turns, we want to spread those turns around the core as much as possible because it spreads the magnetic flux. Now, I will say that if you have a very large diameter core, okay, with a lot of circumference to it, and you don't have a lot of turns, you want to pack them together. But you might want to then use a toroid that's got a slightly smaller circumference so that you can spread those turns out, and yet on the inside wall, they're all adjacent to each other. That's a pretty good way of winding a TLT. The core can also saturate with high RF power. In other words, it will eventually peter out in terms of being able to deal with any additional power. And if the core heats up, you'll have flux degradation to the point where it may even fail and crack. Now, construction techniques. For CMC, we want to look at the total number of turn capacity of the core. You can't add enough turns. As long as those turns are adjacent to each other on the inside wall, you want to fill it up with turns. The more turns, the better. We look at the turn spacing. We want to form the wire to the toroid. You don't want to have overlaps of the turns. You want to have the bifilar be next to each other consistently. If it's red and black, don't go black and red and black, black and red. You want them red, black, red, black, red, black. You want to fix the loose ends with a piece of cable tie and leave sufficient tails. Wire is cheap. You don't want to have to go back and rewind the thing or solder on some extensions onto it. That only is places for failure. Just give it extra tail. For good winding practices, you want to choose the proper wire gauge and insulation. Stranded is preferable over solid because it gives you more surface area on the conductors. You might want to wrap the toroid with tape if you're using magnetic wire. On TLTs you can do that, but not recommended on CMCs. Again, wind the wire tight, space the turns to cover the core all the way around tightly. If your total turns can't cover the whole core, then pack them tight. Don't nick or chafe the insulation, tie it off cleanly and securely with cable ties, leave long tails. Mount with heat dissipation and vibration in mind. You might not even want to put a TLT in a box, or if you do, give it some way to breathe, some way to dissipate that heat. And of course, you want to heat shrink all exposed conductors. On the construction side of TLTs, to determine the power and impedance conversion ratio, remember that the target SWR is less than 2 to 1 from 3 to 30 megahertz. You want to pick the appropriate toroid, use the right size wire, determine the maximum number of turns, set the turns ratio, build it carefully, tight and even, and then test the SWR for ratio with the appropriate load resistor, which we'll get to shortly. Now, let's look at the effects of overdriving a common mode choke. And this is why I said before, on a bifilar winding, you can have a breakdown between those two adjacent sides of your input coax going around the toroid. The core and wire could heat up, threatening the mount and the box. The core can become magnetically saturated. That makes it ineffective. Higher voltages can damage the insulation. Arcing may begin. The shorted RF output can even damage the transmitter. The SWR goes up rapidly and the output power goes down rapidly. When you see that starting to happen, you need to back off right away and let it cool down. And remember, the heat up time is way less than the cool down time. Symptoms of an overdriven TLT. The core heats up and loses magnetic flux capacity. SWR begins to rise sharply. Power transmission drops sharply. You'll also see spurious RF harmonics showing up. And the FCC spec on that says that the harmonics of your fundamental cannot be any more than 43 dB below that of your fundamental signal level. So it has to be way down in the mud. And it'll start to really come up and show up as the whole thing heats up. At the extreme, the core may crack and fail. So let's take a look at this picture. What's wrong with this picture? It's a CMC, and I'm winding it with bifilar winding of this varnished or epoxy outside solid core magnet winding wire. Now, if you don't notice it, take a look right here, and you'll see that there was some rubbing going on when this was mounted up. And those are both sides of the input. Well, guess what? At low power, no problem. Worked just fine with the DC continuity check, so there was no opens. But once he brought the power up further and further, it started to arc across here, and it totally messed up his SWR and his power output. So beware. That's why I say for CMCs and bifilar windings, do not use magnet wire. So let's now talk about testing these devices. CMCs. Here's a little tip I like to use. I built a set of quick NanoVNA calibrators. Remember we said we want to do an open, short, and load check? For most SWR checks, you want to do all three. If you get a switch, which is a single pole, double throw, center off switch, and you get 3 of them, you can build 3 of these, one for SMA, one for BNC, one for the SO239 here. And on one side, you'd have a short that you can see here. The other side, you hook it up through a 50 ohm 1% resistor to ground. And the middle is where the input pin from your connector comes into the switch. And here it's in the open position, here it's in the short position. Think of this toggle switch as an arm that goes down to the left side, to the short side, and if I flip it the other way, that arm continues through the switch to connect to this side, this pole, or this throw I should say, in this case through the resistor and back here to ground. So this makes open short load calibration of NanoVNAs a snap. So let's look at how to use that. For measuring CMC suppression, common mode suppression, we calibrate using OSL-T, open short load through calibration. We set the NanoVNA to log mag. We select channel number 2 to read the through value. The suppression should be more than 25 dB down from 0 dB, and we can save that as an H2P touchstone file because we're using port 2 for measuring through signal. Now I want you to notice we basically jumper the ground side of both ports together, and the center pin only gets connected to both leads on the input, and then the center pin of port 2 gets connected to both leads on the output. Why is that? Well, we are trying to drive current in the same direction through both sides of the CMC. And the CMC is really there to try to resist that flow of current. And you want to see how good a job it's doing resisting that flow of current at common mode. That's why it's called common mode current on both sides of the connection. So here is a CMC test of a bisectional bifilar CMC. Here's the insertion loss. You can see 0 dB. It's darn near nothing. But the common mode suppression in dB, if this is -10, -20, -30, from 3 megahertz up to 30 megahertz, all of it is below -30, which is well below -25. So I am suppressing it well quite a bit more than my -25 desired. Measuring the CMC insertion loss that you saw previously, is you would do the same thing, but now you would hook it up in a more traditional manner where the ground to ground, the center pin to the other side, and same thing, center pin here to center pin and ground to ground, and you set it up the same way. Insertion loss should be less than 1 dB down from ideal, and as you saw earlier, it was almost nothing. Testing TLTs. Measuring the impedance ratio, as we saw before, on port 1, we set it up to basically just the same as measuring SWR, because that's what we're doing. We're looking for the resistance conversion from 50 ohms to whatever resistance we expect to have to use out here at our antenna end. On a 9-to-1 UnUns, that would be a 450 ohm 1% resistor. Ideally, we present that across the output of the TLT, and we should be somewhere in the range of about SWR of 1 or so, certainly below 2. And we can save that as an S1P touchstone file because we're only using port 1. On insertion loss, we have to do a little trick. Because our TLT will convert from low impedance typically to a high impedance output, both ports are expecting to see 50 ohms. So we need to convert it back down to 50 ohms. So we use an identical TLT, but back-to-back, wired back-to-back, so that the high impedance ends of both TLTs are connected together. And that brings us back down to 50 ohms. And then we can measure the insertion loss and divide it by 2, and that's the insertion loss per device. Testing TLTs for power handling. This is really important because, as I mentioned earlier, you have to be very cognizant of when you're pushing the bounds of that TLT in terms of power handling. So, as I said, you would measure it with identical TLTs wired back to back to preserve that 50 ohm impedance of the NanoVNA. We want to run it through an SWR power meter in our test to a dummy load. And that's our setup. We key down on the transmitter in CW mode for 30 seconds. We can use a laser thermometer to measure the core temperature, use a tiny spectrum analyzer to detect harmonics. Now, we want to abort if any of these happen. If the power gets to half of the preset rig output, if the core temperature reaches 100 C, or if the harmonics get higher than 43 dB below the fundamental. Those are indicators. When I say power gets to half of the preset rig, if I set it to 100 watts and it's come down to 50 watts, you definitely want to abort the test. And you know that's the hard limit stop of power handling in that mode, which is CW, which is of course key down. It's the worst case 100% duty factor. You can derate that a little bit, give yourself some room if you're using sideband, or you're using CW in your normal condition, which you're keying down maybe a third or half the time, and then you're listening quite a bit of the time, probably at least as much as you're transmitting. So, but the worst case is a full key down condition. So you're looking to measure the worst case, and then you can compensate for that. So, this is a QR code for this presentation in PDF for your reference, and this is a QR code for my TennaTalk series on the Antenna Whisperer YouTube channel. I invite you to explore both of those and enjoy those. TennaTalk is a continually growing series of talks on all things antenna, and with that, I hope you have a great day, and I wish you 73. Bye-bye.